Welcome everyone to today's webinar. We're going to be talking about validating attack technique coverage using EDR telemetry. This is a reprise of our ATT&CK talk that we gave last October. So thank you to the folks at MITRE Attack and ATT&CK for letting us talk at your conference. We wanted to provide this again as a webinar and also to add a little bit of additional content based on conversations we had after we gave this the first time. So the first thing is we want to know a little more about you. We want to understand, do you perform validation? Is it your full-time job? Is it just a thing that you kind of do on the side? Or no, but you're curious to learn. And this is a thing we're very interested in learning about the rest of the community, is how many folks are full-time devoted to this, or if it's just like a, yeah, I do it, but only when I actually have time. All right, so I'm Adam Ostrich.
Hey, I'm Jesse Brown.
We are both senior detection validation engineers at Red Canary. The detection validation team, more of like a research engineering or research and development type of team. We have a combination of cybersecurity and software engineering skill sets. And our charge is to understand how things should work, make sure things work like they should, and make things work better. That is a very vague thing, which has sort of a lot of broad-reaching consequences across the company, but it also very much motivates why we are interested in validating EDR telemetry. So to start off, we're going to talk about what is EDR telemetry, make sure everyone's up to speed, share how we think about it. We're going to talk about how Red Canary works and how we use EDR telemetry to detect threats in our platform. We're going to talk about our approach to validating attack techniques, where instead of going through like individual techniques one by one and testing them out, what we prefer to do is we take the attack techniques, break them down to their base data components, and then validate those. And then we can sort of remix those to understand what types of things we can and can't detect with this telemetry. We're going to discuss our automated validation workflow we put together, a lot of tooling to help us perform automated functional testing and analysis of all the results of this testing, and then discuss some lessons learned, things that we thought were interesting that we wanted to share with the community. And then as a webinar exclusive, we wanted to talk about getting started with validation and then share some of our thoughts on the MITRE attack framework itself. All right. Cool. So I see some people actually do it full-time and some people do it part-time. And welcome everyone. Hopefully you'll find something interesting in this that'll help you with your job in understanding EDR telemetry or validation systems. All right, so to start off, what is EDR telemetry? So at its most basic level, EDR telemetry is just a representation of behavior on an operating system for security purposes, so you can try to identify when a bad thing happens. EDR, or endpoint detection and response, is comprised of a lot of different things, but the things that I really care about is they have a sensor on an endpoint, and when it thinks a bad thing happened, it generates an alert. In addition, in real time, it streams EDR telemetry so that when you get your alert, you can then go to your cloud portal, hunt through this telemetry, and try to get a sense of, if the alert is actually a real thing or a false positive. So why does EDR telemetry exist? So my understanding is that, right, back in the day, when you think a bad thing happened on an endpoint, really the only main response you could perform is to grab a forensic image of that computer. So dump everything in a process memory, grab everything off the hard drive, create a very large and very complete haystack in which you're trying to find a needle. The depth of coverage here was really, really great, but the cost of collection was very high. It would take a lot of time, it would take a lot of compute resources. You couldn't really use that computer for other things while you're grabbing the forensic image. What people found is that while it's great to have a very large complete set of data, only a much smaller subset of that data was generally used for hunting. And that's kind of where EDR telemetry was born. So by definition, EDR telemetry is filtered telemetry. It's figuring out how can you cut out a whole bunch of things to then ideally have only the telemetry that you need. But because of that, you're then creating all of these edge cases. And studying these edge cases is really important when you're using EDR telemetry for hunting, detections, that type of thing. So another way to talk about EDR telemetry and what it is to go over some of the types of telemetry you'll see from certain actions. So in this example, we have someone who's created a remote PowerShell connection into a computer, and then they're running this command to dump LSAS out of memory to hopefully steal some credentials. So the initial remote PowerShell connection into WSM Profhost is going to generate network connection telemetry. When PowerShell.exe actually executes this command, you're going to see script load telemetry to see not just that PowerShell is running, but what it's actually doing. When procdump.exe is launched right from disk into a process, we're going to see process start telemetry. When proc dump starts loading DLLs like kernel32.dll, you're going to get module load telemetry. You have to accept your EULA to actually run this, which is a registry key in the Windows registry. So to modify that, you're then going to see registry modification telemetry. When you actually access LSAS's process memory space, you're going to see cross-proc or cross-process telemetry. And then finally, when we write the contents of LSAS's memory space to lsas.dump on the disk, we're going to see file create telemetry. So from this perspective, we get a good sense of really a lot of rich information that EDR telemetry is providing about all of these different behaviors. But there are some blind spots. So the first blind spot is the depth of information that you're going to see. So when procdump.exe accesses LSAS's process memory space, you're going to be doing it using system API calls. I think some of them are located in kernel32.dll. But you're not going to see those individual API calls. You're just going to see the cross-proc saying that a thing happened. So I think of it as a more traditional behavioral signature where these 5 API calls in a row means that a bad thing happened. Doesn't really work the same way in EDR telemetry. At the same time, there's certain types of actions you're not going to see. So right after your attacker has dumped LSAS to disk, it's then probably going to slurp it up with PowerShell. And you're not going to see file open telemetry because it's very noisy, and it's usually highly filtered if you'll see it at all. And a good example for why that is that in Windows, if you open up a directory within a window or Explorer window, and there's 1,000 files in that directory, you've just generated 1,000 pieces of file open telemetry, which are not interesting, not really useful for anything. So it's going to get filtered, but there are times when this would be useful, which we'll talk a little more about later. And then finally, at its most basic level, EDR telemetry is just JSON. It's a bunch of flat text with key value pairs describing the metadata around a specific event that happened on the operating system. So here we have process start telemetry, and we just get information like what was the command line, process hash, name, path PID, that type of thing. An actual piece of telemetry would have a lot more data that we couldn't fit nicely on the slide, but this is the basic level of detail that you'll get from EDR telemetry. And now Jesse is going to talk about how Red Canary takes EDR telemetry into its platform to actually detect threats.
Thanks, Adam. So as Adam just described, EDR telemetry is usually JSON, or at least for the sake of this conversation, we'll use JSON as the example. And usually it's a lot of JSON. So at Red Canary, and I imagine many of you too, we've developed a data processing pipeline to handle this telemetry. So but why am I talking about a data processing pipeline right now? Well, it's because we believe that by understanding your data processing pipeline, you can figure out windows into that pipeline where you can insert validation. So we'll give an example here of our data processing pipeline. At a high level, you have various data sources feeding into a standardization phase on the left. To Mark's question, we're constraining this to EDR telemetry, but we'll also ingest things like cloud logs or alerts from other platforms, and then standardize them to a common model. So in the open source community, there's a few standards out there, like Elastic's common schema, or Splunk's common event format, or OCSF, like the Open Cybersecurity Schema Framework. They all solve this problem of trying to normalize all these different ways that data, different vendors, talk about data. And the reason we do this, and I imagine many of you do too, is that it gives your detection analytics the ability to operate on those standardized models. And then through that, you can create alerts. Or at Red Canary, we call our own internal alerts tip-offs. So after those alerts are generated, for us, they get fed into a portal, something like Analyst Workbench, where detection engineers, threat hunters respond to threats. For you, maybe that's Splunk, or something like that. So we'd like to suggest there's two great places to inject some validation. One is right around that standardization phase, where you get to validate data components. And then the next being right after the detection analytics, where you get to validate that those analytics are actually working as expected. So let's double click into that standardization phase really quick. So this is just a really fancy way of saying we're mapping input fields to that common model. And you might be asking yourself, like, this sounds familiar, but like, how does this relate to attack and validation? Well, these are essentially like attack data components. So data components being like one of the more recent additions to attack and like one of my favorites. Data components are essentially normalized or standardized models which MITRE and attack use to talk about similar data types across different data sources. So they can say things like process creation. They don't need to say, process start in the case for Sentinel-1, et cetera. And I like to think about them as software dependencies. So, if you're writing a piece of software, maybe in Python, and it goes out and makes a web request using the Python request module, that Python request module is a software dependency. So if there's a bug in that request module, like your software has unpredictable behaviors. So the analogy that I like to use is that the data components are your detection analytic dependencies. Without those, requisite data components, they won't function as they should. So attack does a great job of documenting which data components can be used to detect various techniques, and they give a lot of great examples. So, we'll stick with like our favorite example, OS credential dumping LSASS memory using procdump. And by the way, so these data components, they're at the bottom of the attack page, right above the references. And the cool thing is they break them down into different data components. A lot of them map to EDR telemetry too. So things like process creation, command execution, process access, file modifications, just like Adam was talking about earlier. So one way to look at this is to take all those data components. And what we did is we took them, and on the y-axis, you'll see data components. And then we looked for commonality between attack techniques. So on the x-axis, you have the percentage of enterprise attack techniques that have dependencies on these data components. So luckily for us, there's a lot of overlap here, which makes it seem like this problem should be pretty easy, particularly if you want to just validate data components, with things like command accounting for roughly 43% of attack techniques. But, if we want to break the attack techniques down into data components, it's pretty easy to spin up, maybe say one VM with a sensor on it. We'll just we'll test something like a file modification and isolation. And it might be easy to say okay, everything's good to go. File modifications look great. We're kind of forgetting about our real operating environment. So we probably all have that server 2012 cluster or the CentOS 6 server that has all the production data on it. And then if that gets popped, that's going to be a bad day for everybody. So what we believe is it's important that your test environment reflects your operating environment, at least as well as you can. So there might be certain cases where sensors don't support all the data components that you might want to use in detection analytics. So that the case might be, with a end of life OS or something. And in that case, your detection analytics kind of have to fall back to maybe a second or third order data component, to detect a particular technique. So that's, that sounds like a tough problem to crack. And how do we figure out, data component support across a variety of sensors and OSs? So some EDRs do a good job of documenting, the sensor and OS support for data components. Some don't. I think some of this comes to back to the idea of publicly documenting blind spots. That could be seen as giving an adversary the easy button. And it's easy, for me to get frustrated when I don't see great documentation. But, it's also, even if it's there and it's great, there's still all these other possibilities that could stop that data component from being usable. So there could be bugs in code somewhere, maybe the EDR, or maybe your own software. So what we found is the best way to approach this problem is just to do functional testing. And that's going to help determine data component availability. And also, we'll work in some threat detection as well to make sure different parts of the pipeline are working as expected. What we'd love to offer you is a bunch of code you could take home and just plop into your environment and it works. But the reality is we all work with different tech stacks and it probably require a lot of retooling. So what we'd like to offer is kind of a conversation about how we approach the problem and how you might think about approaching it in your own environment if you're not already doing so. So for us, at a high level, we'll break this out into four steps. We'll run a functional test. We'll report on expected results. Then we'll compare the expected results to the actual results. And then we'll save the outcomes of those tests for historic purposes to detect changes or regressions. And you can do this all manually, but it really doesn't scale well. And there's some other issues with that as well. So what we'd like to suggest is using automation and using as much as possible. And automation gives us a few things. So it makes the testing repeatable, but it also reduces friction. So if you want to go and write a new test, you can go and write that new test easily. You don't need to focus on specifics about the sensor or the OS. It's all self-contained in that one test that you want to write. So Adam will also talk later about how automating the analysis and reporting process is key to reduce friction too. This is all great, but it has to be usable at the end of the day. So reducing that friction we found is really key. But yeah, so we've broken our validation pipeline into three main steps. The first being spinning up infrastructure, the second being running the test, and then the third being analyzing the results. And I'll speak to the first two steps of this pipeline, and then Adam will pick it up and talk more about the final step here. So when we're spinning up infrastructure, for us, we're spinning this up in AWS, specifically in ECS, and using a tool that we've called CoalMine, which a close colleague of ours, George Allen, being the primary author, developed. CoalMine has two main concerns. So the first is spinning up infrastructure, and then the second being kicking off and running tests. So for spinning up infrastructure, we would like to suggest using infrastructure as code tools like Terraform. Terraform gives us repeatability, so we can easily spin up and tear resources down. And the way CoalMine works, it's a ECS instance, and the tests will run on a periodic schedule, kind of like with the cron job. And then Adam's also hooked up a really sweet API gateway that can trigger this programmatically too. So we can fit it into other, CI sort of workflows, for validation. And then for configuration and, just configuration management, we use Ansible, and then we'll use Ansible playbooks to install things like EDR sensor and other test prerequisites. CoalMine's last concern is kicking off the tests. So we'll run a variety of community projects like Atomic Red Team, which is great if you want to get started. Atomic Test Harnesses, which kind of dive more deeper into the different variations of techniques. Kind of takes, what MITRE's documented, for different detection analytic ideas and takes it maybe to another level of more variation in the techniques. And then, for this presentation, we'll talk about an internal tool that we call the Vusa. It's just mostly a tool for testing and validating data components and techniques. So we'll double click into the Vusa, or our test execution phase. So this is what we'll use to execute the test, and then also take measurements about data components and also document detection analytics that should have fired. So at this point in the pipeline, we have a test VM. In our case, it's an EC2 instance with an EDR sensor installed on it. And then that sensor is making observations about what's happening in the environment. But we're going to treat it like a black box. And we'll take our own measurements to validate. So we'll use introspection to compare, what happens, to what the EDR observed. So it's going to make Vusa is going to make observations about what it did. Essentially, it will do things like I get my slides in the right order here. It will do things like figure out a process command line, the process PID, hashes, etc. And this is where we can start to see some cracks or potential issues that you might run into, which could affect detection analytics. So the EDR example on the left here returns process paths a little bit differently than how we expected. So if we had detection analytics that relied on the drive letter, prepended to the process path, like that could cause issues. We could also just have like incorrect data, like the case with the process PID here being off by 1. Maybe not super problematic for some, but for us in some cases that becomes like very problematic. So the final thing that the Vusa will do after it's done executing the test is it will compile all the test results into a report, and then it's going to drop that into an S3 bucket, which kicks off the final part of our detection pipeline, validation pipeline, which will analyze all the results. So that expected results report contains things like the sensor ID and other endpoint metadata to help that stage triangulate itself and find data. It will also include the expected detections and also the expected standardized telemetry. So I'll pass things off now over to Adam, and he's going to dive more into this final step of the pipeline where we actually get to compare and report on how well our expected results mapped to what the sensor profiled and what our detection engine detected.
Okay. Thank you, Jesse. So, we've taken our expected results. We've dropped those into this S3 bucket, and that triggers our analysis phase. So dropping the data in there kicks off our telemetry validation Lambda function. And if you're not familiar with Lambda functions, this is just serverless code inside of AWS. It's really just a bunch of Python scripts. And what it does is it goes back and takes all the sensor data generated by the Vusa that's already gone to our production engine, and it just grabs the data associated with that test run. So it grabs all the native telemetry, grabs all the standardized telemetry, and it grabs all the tip-offs or alerts. So the main thing that this function does, it's about analysis. But an important thing to note is that the point of this is less to say, do things look good or do things look bad? It's more about taking measurements that we analyze at a later stage. So the first type of measurement that we take is something we call telemetry profile. And the idea is that we go through every single event type, every single field in each event type, and just determine the percentage of time that data is actually filled in. This is really important when you have things with standardized telemetry, where maybe not every field will be provided by every telemetry source. A good example is there's one specific sensor that never includes a parent process path inside of a process start record. So if somebody creates a detection analytic looking for parent process path, they have now accidentally excluded an entire sensor and therefore entire part of our customer base, which we don't want to do. Typically, this has been handled using institutional knowledge. You just kind of knew it, or if you didn't, you make a mistake, someone fixes it for you. But a better way of doing this is to take these sort of real-time measurements and then make this available to detection engineers as part of their workflow. The next thing, and sort of the main part of this function, is we compare our expected results to our engine data. And for things like detection analytics, it's pretty simple. We expect detection analytic 1, 2, 3, 4 to fire. We then look through our tip-offs. We say, hey, look, 1 is for detection analytic 1, 2, 3, 4. We're good to go. For standardized telemetry, this gets a lot messier for a few different reasons. So we start off with a list of results we expect to see, right? The fields that we expect to actually be there. And then we try to match them to pieces of telemetry, but maybe not all the fields are going to be in every single piece of telemetry. Maybe there's a mismatch in specific fields. And when to find the correct piece of telemetry, then note that mismatch. Or maybe that piece of telemetry isn't actually going to be in our system at all. So how do we approach this problem? So the first thing we do is we just kind of do a dumb approach of let's compare field by field and see if they match or don't match. So if the fields match, we call it a valid result. If the fields don't match, we call it an invalid result. And then we just assume that the piece of telemetry with the highest number of matches is probably the correct piece of telemetry. But then there are some edge cases we have to take care of. So the first one is, right, not every piece of telemetry will have every single expected field. A good example for this are hashes. So EDR telemetry sources will often give us an MD5 hash, maybe a SHA-256 hash, but not the SHA-1 hash. So one or two of those hashes, but never all three. So we want to make sure that if the data is never going to be there, we'll skip those so it doesn't count against us as we're trying to match things. The other thing we do is we have to weight these matches differently. And I think a good example is, say, in a process start record, the process PID matching is a much more important match than, say, the name of the user that launched the process. So we find the largest number of matches minus fields that we skip. We weight everything differently. And this has proved very effective for us. In our sort of tests, we found that if we're unable to find the correct piece of telemetry associated with what we think we're going to find, it's because it doesn't exist. So a thing I want to talk about, and this is important for validation, and this is important for writing detection analytics too, is understanding the differences between sort of what you expect to find and what you actually find, and how this can vary depending on the specific sensor or the telemetry source you're getting data from. So one good example are Windows directories. So, right, the directory C Windows System 32 might be represented like that, or maybe C, someone says C is actually the letter drive that's mapped to device hard disk volume 1. So telemetry sources will represent the same directory using these different methods. And so you need to be able to account for those. Same thing with script content. Script content does not always match up exactly. It has more to do with, I think the wrapping metadata stuff around it. Think quotation marks, parentheses, that type of thing. And our approach to get around that is to just measure the similarity between two different things. So we use this Python library called difflib.sequencematcher. We basically say if these two fields are 94% the same, that's proved an effective ratio to say, hey, everything looks good. This is probably the right script. Another thing is just Windows registry everything. And this, I think, is a really great example of how a lot of this stuff is not standardized across different telemetry types. So things like paths. HK current users can be HKCU, which might also be HKU or HK users / the SID of that current user. You'll have / registry / user / user. Same path referred to in a lot of different ways. Same thing with value types. So expand SZ might also be represented as expanded _ string or expand string. And even multi-string values, I've seen them be comma delimited. I've even seen them be Unicode null byte delimited. So right, there's just a lot of really big variations in how this data is represented. And you just have to understand all these edge cases to say, yes, this is actually the same thing that I'm looking for. So once we have all of our results, we convert that into a whole bunch of tiny little flat JSON records designed to be easily looked through inside of Splunk. And we drop those into an S3 bucket. Those are then available through an API that I'll talk more about later, but they also get ingested into Splunk, which is where we do most of our analysis. So the Splunk dashboards I've created for this analysis, there's a few different ones. They sort of allow you to zoom in and zoom out in different ways. But this is the view that I wanted to share because this is where I spend most of my time. And I think really shows the value of our entire approach to this. So we have our valid results, our skipped results, and our invalid results. And for each one, we have the specific field name we're looking at, the data that we expected to find, and the data that we actually found. So you look at the valid results, everything looks good. Look at the skipped results. You can see that in this example, we don't get an MD5 hash, or we do get an MD5 hash from the sensor, but we're not going to get, say, SHA-1 and SHA-256. So we skip those, and it doesn't count against us. But then we have our invalid results. And this is the exact same thing that Jesse showed a few slides earlier when talking about Vusa, where this is sort of the way we make that data available to a person, right? The process path, you can see, hey, this is the letter drive C is actually mapped to device hard disk volume 1. So I would see this, and I'd go back to my Lambda function, and I would just add another case statement to say, oh, by the way, if we're matching process path, allow this edge case. But then we have our process PID, and we see that we have this off by 1 error. And right, this is sort of the real power of looking at data from this perspective. This is a contrived example that we've put together for this talk. But this problem right here is a real thing that we found in a sensor, where a new version of a sensor came out. There are a lot of good new features, but there's a tiny little bug that caused a regression in how it actually reports the process PID. This is the type of thing that might be difficult to find. Like, it's subtle. It might take weeks, maybe months to find. But when we're looking at things from this approach, new sensor version came out, suddenly 50 tests started failing, because every time we're looking at a process start record, we don't actually, this data isn't matching. So this has proved very effective for us in looking at sensors and identifying, small regressions in the data that has a really big impact when actually performing detections and analyzing that data. So the next thing we did is to make this data more actionable, to make the system sort of easier to interact with people across the company. We created what we call our validation APIs. And this is just an AWS API gateway. We're hitting specific endpoints, triggers Lambda functions that do different things. So we have one to launch and monitor the status of coal mine jobs. We have another one that will allow us to look at the results of the Lambda function, but also allow us to submit our own sort of results for Vusa from a manual run. So if there's some one-off thing, maybe it's a one-off operating system. I did some stuff looking at container telemetry at one point. And instead of having to incorporate that into coal mine, you can do your one-off run, submit the results, and then take advantage of the automated analysis setup that we put together. And then we have our telemetry profiling Lambda. This is just taking that telemetry profiling data and making it available to detection engineers as they're actually going through their workflow to develop detection analytics, to understand when there might be problems in the analytic they've constructed and how that'll match to the telemetry provided by each source. So now we want to talk about some of our lessons learned. And the first thing just comes down to telemetry quirks, and whether validation, you're performing validation, you're performing detection analytics, understanding these quirks are really, really important to understanding coverage. So the signal to noise ratio is going to be different for every sensor. EDR telemetry by definition is a bunch of filtered stuff, but how that filtering done can vary by quite a bit. In general, higher quality telemetry, things like process starts, often module loads, executables being loaded into memory and then being run, that stuff you're probably going to see not being filtered very much. But lower quality telemetry, things like file mods and reg mods that are uninteresting, some very, very large percentage of the time, are often going to be highly filtered. But the mechanism can be different depending on the sensor. So FOD mod filtering, there's one sensor that actually filters by the number of file mods generated by a given process. So if a process starts generating too many file mods, it starts to filter them out. And then if it keeps generating too many, it just won't show any more from that process until the box reboots. In general, though, file mods are filtered based on the directory and the file type. And I think a really good example of this is on Linux. Everything is a file. So how do you actually determine which file mods are interesting and not interesting? So if you take a text file and you drop it in /temp, you're not doing anything to interact with the operating system, really. That's a very uninteresting action. But if you take a text file and drop it in /etc, where you could potentially change the configuration of the operating system, that is a very interesting action, and that's probably less likely to be filtered. However, there are file types, things like ELF files, Python scripts, shell scripts, generally executables. Those are going to be more interesting no matter where they're dropped. So those file types are less likely to be filtered. Another thing to be aware of is that things like file telemetry have very inconsistent meaning and terminology. So if you back up, think like philosophically, what is a file mod? You have some software that's calling some system API, which is opening a handle to the file, which is then interacting with the index of the hard drive, which is then pointing to part of the hard drive. We're actually going to write the contents. And you have all of these different places where sensors can and do hook and call that a file creation record. There's actually one sensor where when you create a file, you get 3 different file creation records, each with slightly different information. So I think they're hooking all these different things and then sending the data your way. So why do you care? Why is this important? Well, say you're trying to create a system where you're detecting someone dropped malware with this specific hash to disk. Well, do you look for a file creation record or a file modification record? Sometimes a file creation record is really just creating like the infrastructure to then write the file, and then writing the contents of the file to disk is a file modification record. One sensor actually, every single file creation record contains the hash of an empty file, and then you only get the file or the hash of the actual contents in a follow-on file modification record. So right, understanding these types of terminology kind of inconsistencies are really important for any telemetry source that you're dealing with, and understanding how does your sort of perceived understanding of this actually map to how they're representing the data. So challenges of EDR telemetry, it really just comes back to the fact that the level of detail is limited. Right, you get limited insight into certain types of behaviors like API calls. You can't use static binary signatures outside of a hash. So if you think a piece of malware has these 300 bytes in a row, it'll mark it as that piece of malware. If somebody recompiles the file, the hash is going to change. It's going to look completely different to EDR telemetry, but a standard static binary signature could work. And then certain telemetry types are limited because they're noisy. I mentioned file open telemetry earlier, and that's because a few months ago, I was asked to look into credential theft. And is there native telemetry we're getting from sensors that we're not properly standardizing that could help us better capture or catch credential theft? And the answer is no. We were really doing about as well as we could. But the reason why is because when you're looking at things like dumping LSS, we get good telemetry, right? We had our example at the beginning. We're using proc dump, and there's all these different pieces of telemetry that you're getting to represent this behavior. But ultimately, it's really that cross-proc of procdump.exe into LSS's memory space that's going to say, hey, something sketchy is probably going on. You should look into it. But what about things like application credential theft? Think of like browsers, password managers, that type of thing. You're really not going to get much of telemetry because it's really just the wrong process opening the wrong file according to some definition of wrong, right? And the good news, though, is that even though this type of data isn't really going to be in EDR telemetry, EDR sensors are good at jittering alerts for this activity. So they won't send off the telemetry, but EDR sensors have access to a very rich data set on the operating system. The challenge, though, is that EDR sensors are limited in both the number of analytics they can run and the complexity of these analytics that can be run, because they're limited by the compute of an endpoint, which might be an underpowered laptop. So that brings us to some of the benefits of using EDR telemetry, which is that by offloading detections from our endpoints, once you accept some of the limitations of it, you can do a lot of really cool stuff. Now you're not limited by the compute of a given laptop. You're limited by the compute of all of AWS, which is really, really big. We're able to create a very highly scalable detection engine that is able to do things that you just couldn't on a single endpoint. And it's kind of a strategic advantage. By offloading detections from the endpoints, your adversaries can't see alerts. So if you have an adversary that's sophisticated enough to study the security products they're going up against, they're going to see, I performed this action, I generated an alert, maybe I shouldn't do that or I might get caught. And they might be able to see the EDR telemetry they're generating, but they won't know these 5 pieces of telemetry generated an alert that might get caught. Finally, EDR telemetry provides a very versatile representation of behavior. It does a good job of capturing the context of what happened, right? There's a process potentially did a bad thing. Let's reconstruct the process tree and let's grab every single piece of telemetry associated with each process and then provide a very nice picture of that overall behavior. So now we want to talk about, so that was sort of the end of our original attack on talk. And some questions, and I'll say a sentiment that was sort of shared with us is, that's great, that's a bunch of cool tooling, but right, like we asked at the beginning, maybe validation isn't my full-time job, maybe it's a thing that I only do every once in a while when I get a chance. And so, right, the point of this talk isn't to be like, hey, look at our cool tools that you can't have. The point is to sort of share our thought process and our methodology, and then you can adapt that to whatever resources that you have. So the biggest thing with validation is that some validation is better than no validation, right? Doing what you need to do what you can with the resources you have. We have a dedicated team. There's a lot more we would like to do. We just don't have time to do. So we're just limited by our resources. And everyone is, right? But the biggest thing is to start small. So functional testing in VMs is really important, right? Actually running a thing on an operating system and seeing how your entire system responds to it is really, really important. And you can do this locally using, VMware Workstation, VirtualBox. You can even use EC2 instances without any sort of automated way of defining these environments and spinning them up. If you're looking for functional tests to run, Atomic Red Team provides a very nice library of tests to go through and emulate specific behaviors. But starting small, is data even flowing is a really, really important test that you don't need any fancy automation or systems, analysis systems set up. Just, did I do a thing? Did our system respond? And if you want to take that a step further, a good approach to it is targeting high impact data components. So going back to our slide that we showed before, right? If you just run a test that looks at, I ran a command, how does my system respond? I create a process, how does my system respond? Just doing those actually gives you a lot of coverage of a lot of different attack techniques. And so you can go down the list further, right? You can expand how detailed your analysis is. But that's a really good place to start, is really these high impact areas. And then finally, we want to provide a few thoughts on the MITRE attack framework. This is our first attack con that we went to. Something we were, I'll say, amused and a little surprised to see is that a lot of people came in with some very hot takes on the MITRE attack framework. There are a lot of soapboxes about every way that people is misusing it, all the problems with the framework. And this is good for academic discussion about what is the framework. But we wanted to sort of offer our thoughts on what MITRE attack is and how it's useful. And our hot take is just that we like it, we think it's good, but we want to talk about why. So I personally got into cybersecurity a few years before MITRE attack existed. And as I've built up my cybersecurity knowledge and expanded my career, I've actually spent very little time thinking about MITRE attack and looking at MITRE attack. But what it's been very useful for is when I need to communicate with somebody. So if I want to talk about credential theft, it's a little complicated to, I understand credential theft and I can try to communicate what that is to somebody myself, but it's a lot easier to say, hey, go look at this technique. This is credential theft. Here's a bunch of sub-techniques. Here's how you can detect it, this type of thing. And this was actually the original reason why MITRE attack was put together. At ATT&CK, there was a cool panel where the folks who originally came together and said, we were just trying to find a way for offensive folks and defensive folks who understood cybersecurity to find a shared framework that they could use for communication. And this really expands to what this talk is. When we decided to perform our validation into, how do we perform different emulation of threats, we didn't really look at MITRE attack or the enterprise matrix or anything like that. We understood offensive methodology. We understood that the way we were going to detect that is with our EDR telemetry. And we knew that by studying that telemetry, that's going to provide us a really scalable way to understand which threats we can and cannot detect. But then we wanted to talk about it. And sure enough, MITRE attack has this awesome thing called data components, which is a nice sort of corollary to what we're doing with EDR telemetry. So again, it's provided a very useful shared framework with which we can actually communicate. And then finally, MITRE attack is a very effective learning tool. The way I like to think about it, and the way I've heard people talking about, how do you learn a new thing that takes experience? You have to develop a feel for it. And an analogy that I like for it is paint by numbers. So, right, you get some sort of black and white drawing. Each section has a little number in it that says, hey, if there's a 5 here, you paint it blue. If there's a 6 here, you paint it red, that type of thing. And you can do that, and you can go through the motions of fully constructing a painting without actually knowing what you're doing. But then you can go back and reflect on it and say, hey, look, this section is blue because it's the sky. This section is green because it's tree leaves, maybe in spring, or it's orange because it's tree leaves in fall. And the idea is by going through the motions of a thing and then reflecting on what you're doing, you can gain a feel for it and gain experience. And that to me is really what MITRE attack is. I don't really care if it has every single attack technique. If it, it's, the completeness of it is not really important. The point of it is to sort of represent a lot of different ideas and behaviors in a way that somebody can understand, so that you can go on and use that in your own cybersecurity career. All right, so key takeaways, EDR telemetry by definition is a filtered piece or source of telemetry designed to balance the signal to noise ratio. So understanding all the edge cases are really important and knowing what it's good for detecting and what's not good for detecting. Validating attack techniques using data components scales really well, and I think works a little bit better than just trying to go through techniques one by one. End-to-end functional testing is really, really effective. That provides a very clear signal when there's a problem, and it captures a lot of nuances of techniques that you wouldn't get if you're not just running a thing against an operating system. A lot of automation, right? Automating everything you can allows us to scale our validation to lots of sensors, lots of operating systems. The con, going back to this again, right? EDR telemetry provides a limited level of detail, but the pro is that once you offload detections from endpoints, you're able to scale your detection capabilities and provide a lot of context around alerts. If you're trying to get started with validation, really just worry about starting small with functional testing and expand when and where you can. And then ultimately, right, MITRE ATT&CK, I don't think it needs to be complete. It just needs to be an effective tool for communicating and for learning. And that is everything we have. We have a blog series that we've started putting together called the Validated Canary. There's a couple links to these. Hopefully we're going to have some follow-on blog posts, really just echoing some of the things we talked about at this talk a little more, talking about the Vusa and so our analysis workflow. But I think that is everything that we have. Are there any questions from anybody? Either I think you could submit it as a question, or I don't know if you can pop off of mute and ask it in person, but we're happy to answer any questions you might have.
Yeah, you guys knocked a lot of them out that were in the chat. If you want to rehash one of those, feel free. Otherwise, I think we're probably good. We're just at about time, so no worries if not.
Okay. Yeah, I think, yeah, unless, see, Mark asked a lot of questions. If you have any follow-ups that either I or Jesse didn't answer to your satisfaction, we're happy to dig into that. Thank you for your engagement, by the way, Mark.
Yes. Yeah, we'd love to just have conversations too. So reach out on, I think, LinkedIn or anywhere if other things come up. I know. Like,
yeah, we have this after.
Oh,
so go ahead, Jesse.
Oh, I was just gonna say, like one common question we get, and a problem that we've struggled a lot with is like how do we deal with situations where there's like some sort of filtering on data that's affecting attack coverage. I'm assuming that's like probably a pretty common issue a lot of people run into. Oh yes, and Mark, that the blog on Vusa is on my plate, and it is coming. And I don't know if I have an ETA, but now that you've asked, it's bumped it up the priority list for me. So when it with filtering, like it's like a tricky problem. If you're using something like Sysmon, you can go and adjust the configurations, and you're mostly good to go in most cases. But with like more traditional like EDR sensors, like there's sometimes configurations, we'll dig through documentation, see if maybe there's something, sometimes just talking with the support personnel, or if we can get a conversation going with the developers behind the sensor or a threat research team. Usually those end up being really productive. But I think not everyone like has that luxury, I guess. So like the other thing we'll do too, like particularly if we just like can't work around a particular problem, is we'll like look for other data sources. Sometimes it could be thinking about the detection analytic in a different way, but it could also be like looking outside. So looking at alerts that EDR might be generating. Sometimes they might be completely noisy and terrible, but then other cases maybe they're like exactly what we're looking for, like Adam was talking about. With credential theft. Oh yes, Dave, thank you so much. I miss you too. And yes, so the webinar will be available, I think shortly, maybe potentially this afternoon for download.
And I guess, Mark, to answer your question about baselining, and I think this is maybe what you're getting at, is that, right, functional testing is good because you're interacting with an operating system, but like spinning up a fresh Windows EC2 instance is not the same as looking at running these things on some server that's doing a crazy amount of things. And the answer really is that we don't account for that. That would be a cool thing to do at some point, but doing that realistically, I would claim is nearly impossible. I think like you can make efforts to say, okay, this is busy in this way, or this is busy in this way. But the main thing we do is we try to make sure our testing is thorough enough to understand edge cases, right? So a good example was the sensor that started filtering out file mods based on the activity of the process. We actually originally noticed that because we weren't rebooting after setting up the system and then running Vusa, which meant that Ansible going to Python, performing 1,000 file mods, meant that Python never logged any more file mods. And then we ran Vusa, there was nothing there. So we're able to exercise things that will suss out realistic behaviors, I would say, and limitations. But ultimately, right, there's always going to be edge cases that can pop up where it's like, okay, we've done our best, but maybe, you know, this doesn't help in this case, I guess. But the goal is at least, I think, like to start with a baseline of knowledge. A lot of this is more about improving our understanding of EDR telemetry so that when someone comes to our team and they're like, hey, this isn't happening, you know, we're not detecting this, why not? We at least have a certain amount of knowledge we can then go into the situation with and then perform more analysis to better understand.
Awesome. Well, I think we're at time. So if you have any additional questions, feel free to ask them here. We will see them once we're logged off. Otherwise, you can contact Adam or Jesse via LinkedIn. We really appreciate everyone's time today. Thanks for attending. And that is all we have. Have a great rest of your day.